process, right? So the data has to be prepared in a certain sequence, and the steps involved in that sequence is shown in this flow chart. Could you able to see this flow chart? Process flow chart. Process flow chart is visible. Is it visible?
Visible,
Yes.
sir. It's visible.
So first you have to start with the CAD model, whatever the component you want to print in additive manufacturing. You have to develop a CAD model using a software, CAD software. Then you have to convert the CAD model into a STL file, which is a standard format for additive manufacturing. Why we require a STL, we have discussed. Then after the STL file is prepared, you have to orient the part for minimal support, better strength, better finish, and less material consumption. So once the part orientation is identified, depends on the path orientation downward facing surface, support structure are generated. There are different designs in which you can generate a support structure. Then the part as well as the support will be sliced layer by layer by slicing. So there are a different way in which you can do a slicing: positive tolerance, negative tolerance, top to bottom approach, bottom to top approach, adaptive slicing, and uniform slicing. And slicing thickness is very critical. It depends upon your mission parameter also. In continuation of that, in today's session, we are going to discuss the sixth topic, which is tool path generation. So from first to six, it is done using a virtual method. That is, by using software, you will be performing. None of the steps are performed experimentally. So if you want to do some computational based research or J component, it is advisable to take a topic from 1 to 6 between CAD model to tool path generation. Part fabrication will be doing physically. So different principles are there, which falls under 7 types of AM classification. So according to your need, you can select a suitable principle. Then after printing, based on the principle, you have to use a post-processing method. So this too has to be done using a physical hardware setup, right? So today, what we are going to discuss, we are going to discuss tool path generation. What is tool path? Why we require a tool path, and what are the different types of tool path available for printing, and pros and cons of each of those tool paths. Is this slide is visible? Tool path generation. Is it visible? Tool path generation.
No. Now it's visible. Now it's visible.
Okay. So the sixth step in data processing is tool path generation. That is, within each layer, how the material is deposited. We have a CAD model, we have generated a support, we oriented it, and we sliced. So each and every 2D contour has to be printed, right? There are different way in which you can print a component. For example, if you look into this horse figure, let us say, so if you look into this image, you can see the animated image. So it is moving on some path to deposit a material. So you have to print a square. Within a square, you have a hollow cylinder. So you have to print a square and circle. Between the square and circle, you have to deposit a material. So in different way, you can deposit. So what are those way, and what is the impact of this different strategy that we will be discussing under tool path generation? To make it in a simple manner, let us say this is one cross section. It is a 3D model of a horse, but the image shown here is one particular cross section. So top view of the horse, which is going to be printed, that cross section is shown. It is 2D contour. As of now, it is 2D contour. So if I want to print a material, or if I want to deposit a material within this 2D contour, it can be done in different way. For example, I can deposit a material like this, line by line, according to the profile. That is, within the profile, I will be depositing, or I will move my laser, or I will apply a glue for paper. Finally, I'll get a horse shape, the same 2D contour. Or I can fill like this, zigzag line. So at the end of the day, the contour is same, but what is the path you are going to choose? In which path you are going to generate a material, or in which path you are going to use a laser? Or you can use contour scanning. That is, you start with internal core structure, then concentrically you deposit a material within the profile. So in all three image, you will be getting a same component. You will be getting a same contour, but within the contour, how you are going to fill, that is very critical. So that is what the selection of suitable path is discussed in this session. That is tool path generation and what is the impact of different tool path generation. Now, uh, there are a different way in which you can generate a tool path. For example, if suppose if I give a square outline, printed outline to all of you, and if I give a color to color within the square, each one of you will start to color in different way, different direction. For example, some of you will try to give color in this direction. Some of you will try to give color in this direction. Some of you will try to give color in this direction. So it is not necessary that always everyone will follow the same hand movement. Hand movement varies from person to person. The way in which you are depositing, the way in which you are moving your hand will reflect on the finish of our color, right? Some of you may apply a color on a paper, then that paper has can be swiped across the paper that is within the contour to get a color image. So at the end of the day, the outline is same. All of you will be giving a green color square, but the filling method will reflect on the finish of your color. So there are different method in additive manufacturing in which you can fill or deposit or join the material. And among the different methods, some commercially reputed method, commercially used method in most of the machine is shown in this: raster scanning, perimeter scanning, directional scanning, zigzag scanning, line by line scanning, area by area scanning, boundary cutting. So these are all some standard commercial method which are used for depositing a material: raster, perimeter, directional, zigzag, line by line, area by area, and boundary cutting. So what is this and how one is different from other, that we will discuss in subsequent slide. The first scanning strategy is raster scanning. So if you look into this figure, would you all able to see this slide, raster scanning? The raster scanning slide is visible?
Yes, sir.
Yes, sir. Okay. So if you look into the sketch which I have done, this is the CAD model which I want to print. Okay, so the CAD model which I want to print is shown here. So I will be completing my CAD model, convert it into STL file, and I will be printing in this orientation layer by layer. So after orientation, and it will generate a support structure, then I will be slicing this model into n number of layer. So the green color line which I am drawing is n number of slice. So one slice top view is shown here. The top view of one particular size is shown here. So the top view of one particular slice. So this is the CAD model, and after slicing, the first slice is shown here. So this is what you have to print. So internally, it should be a cavity, and the contour for first slice is this according to the CAD model. And within this line and the circle, you have to fill a material. Could you all able to visualize this layer CAD model on the top view, right? So how I am going to deposit a material? The first method is a raster scanning method. In raster scanning method, between the contour, I will be filling a material, or I will be using my laser to join a material, or I have a paper and I will apply a glue in this manner. So first I will apply a glue in vertical direction, then I will apply a glue in horizontal direction. Between one line to another line, you have a spacing. So that spacing depends upon your density requirement. So whatever the density you required, and based on the density, you can leave the distance between one line to another line, like we have seen in FDM process, air gap. So air gap is nothing but spacing between one line to another line. So this is one type of strategy. First, it will draw a line within the contour vertically, then it will draw a line, or it will apply a material, or it will deposit a material, because we have different principle. Either using a laser you join, or using a UV light you join. So these lines represent the path in which the joining mechanism happens. The second strategy is a perimeter scanning strategy. For all image, I'll be using the same contour, that is top view of this model. So the second strategy is a perimeter scanning strategy. In perimeter scanning strategy, first the laser or the material will first generate a contour. So it will generate a contour first. So this is my contour for first layer of a CAD model shown in the previous slide. And within the contour, again it will follow same strategy. It will deposit or join the material vertically, then it will deposit and join the material horizontally. The distance between one line to another line is a spacing, and spacing control the density of a component. What is the difference between the previous slide and the current slide? In the previous slide, raster scanning, we will be doing only the vertical and horizontal lines. It doesn't care about the printing of material at the contour. But perimeter scanning will take care of vertical, horizontal, like a raster, and also it will give focus on the contour. So obviously, the first one will take less time because it is printing only the region. Second, it is printing the region as well as it is giving connectivity at the contour. So this will take higher time compared to the raster scanning. But finish wise, since you are going to give a skin contour also, the finish of perimeter scanning will be better than the raster scanning. So it depends upon your need, whether you have a time constraint or you want to do it rapidly, or you need a better finish. So based on that, you can select a perimeter scanning or raster scanning. The third strategy is the directional scanning strategy. Directional scanning strategy, what it will do, again for the same image, first it will print or it will deposit a material at the contour. Then within the contour, as different from the previous case, in the previous case, it will join horizontally and vertically. But in this case, it will join diagonally. So diagonally, it will connect a material, or diagonally, it will deposit a material. If suppose if you have a 36 layer, right, and some case you can divide 360 by 30, right? So you will be getting 10. So from all the layer, it will keep on. For example, first layer it will print at 0. Second layer it will print at 36 degree. Third layer it will print at 72 degree. Then it will print at 108. So you can keep on varying. What is the purpose of this strategy? Because in first two strategy, your material is connected only in vertical and horizontal direction. So in principal direction, it will have a better mechanical property, but on diagonal direction, for example, in shear, the first two strategy may not give better strength. The third strategy will give better strength. Sometime if you need same property in all direction, then you divide number of layer divided by 360, and based on the value you keep on change the angle. First maybe 0 degree, then 36, then 72, so that you will be getting continuity in material in all layers, so that the material can behave somewhat isotropic compared to the first two method. So that is the need of directional scanning. Directional scanning will print a material in all direction, so that you will get the same property irrespective of printed strategy. Next, the strategy is zigzag strategy. Zigzag strategy uh, same like it will print a contour, and within the contour you can go for multiple lines, that is contour width. If you need high strength material at the or high bending strength material, because if you add more material at the contour, then the bending strength will be more. So if you need, based on the strength requirement, you can deposit multiple contours, maybe 2, 5, 8. Then within the contour the material will be filled like this zigzag. So how it is different from the other case? In other case, each and every time the material deposit, then the nozzle ideal, then deposit, then the nozzle ideal, then deposit, nozzle ideal, then deposit. So there is lot of ideal time between one line to another line in the previous three cases. But in this cases, from starting to end within the contour, there is no ideal time for printing method. There is no ideal time for laser fusioning. There is no ideal time for applying a binder. So it will be done continuously, and this is predominant method used in FDM process. What is FDM? You have a filament melted and deposited continuously. So at each and every line you cannot deposit a material, then cut a filament, then and so you change a raster angle. This is called a raster angle, right? For example, if you need same strength in all direction, then divide entire height divided by 360. 360 divided by entire height. So uh, that is what you can do in zigzag strategy. The next strategy is line by line strategy. In line by line strategy, irrespective of your design, always the material will start to bind, or always the material will start to fuse from left to right, line by line. Only vertical line, there is no horizontal line. In raster we have both vertical and horizontal, but in this case we have only vertical line. So this strategy is mainly used in 3D printing process. We have discussed 3D printing. In 3D printing, what we will do, we have a powder. On the top of the powder you have a cartridge which will eject a glue. So this cartridge is similar to 2D printer. In 2D printer, once you prepare a document, the printer always print a line, first line to last line. That is what it will do, right? If you type a document in a page, and after typing, if you try to print, first it will print a first line, second line. There is no chance of going for zigzag, directional, or raster. So you have only one option, that is line by line you have to print. So this strategy is mainly used in binder jetting process, or any process which have a cartridge. Cartridge will eject from left to right or top to bottom. Always the cartridge will eject left to right, top to bottom. Right. So another category I think you all could able to see. We have discussed a process called LOM, laminated object manufacturing. You take a sheet, then cut a sheet, then cut a contour. Between the contour and the part, you make crisscross sheet lamination process, right? So that strategy is called boundary cutting strategy. You take a sheet, create an envelope based on maximum X and Y axis, cut a sheet as per the particular contour. Within the boundary and the contour, already this sheet is connected. The white color region is already connected. You no need to deposit any material because already it is a sheet. You are going to contour a sheet. Between the contour and envelope, you make a crisscross cut. So this crisscross is used for support. And after printing, you can easily remove it. So this strategy is mainly used in LOM process, and technically this particular strategy is called boundary cutting. You cut a boundary, cut a envelope, between the boundary and envelope you make a crisscross region for support. Then the last strategy is area by area solidification. So that process we'll be discussing now. So in this strategy, there will not be any laser, line, or binding mechanism. You spread a powder. So whatever the dots you are seeing, you will spread a powder. Here also it will be powder. In the white color region also, which will be powder. Then On the top of the powder, you create a mask, electrically charged mask. And according to your slice, you charge this mask. So wherever the mask is not covered, on the top of the mask there will be a light, UV light. So the UV light UV light will pass onto this mask. Wherever you have a opening, the light will pass and it will join the powder. Wherever you have a restriction, the light will not pass. So the powder will remain as a powder, or the resin will remain as a resin. It can be a powder or resin. And using, so HP, the 2D printer HP is there, right? So they have recently ventured into 3-dimensional printer. So the HP machine is using this technology, similar technology. So you spread a powder on the top of mask, electronically charged mask, and this mask will allow certain region according to the contour. On the top of the mask, you'll have a UV light. So once you charge the electronic plate as per the contour, wherever you have a restriction, the light will not pass. So beneath the mask, the powder or resin will remain as a resin. And wherever you have a you do not have a restriction, the light will pass and you get a cured region. So this particular strategy about the strategy and based on needs. Shall we see the Cura? Yes. Cura screen is visible. Cura software is hello. Hello.
No, sir.
Is Cura, please let me know so that I proceed further.
Yes, sir. Now the screen is visible. Cura screen is visible.
Okay, thank you. So now we have discussed the tool path. That is the last part of our data processing in module 2. So we will see how the tool path is defined in software. So as we have done earlier, file, open the file. So here I'll be importing the same turbine model. So turbine blade, I'll be loading. Could you all able to see the turbine model? Yes. Could you all able to see the turbine model?
Yes,
Yes,
sir.
sir.
Yes, is it visible, turbine model?
Yes, sir.
Yes, sir. It is visible.
So once you load, you have to do a path orientation and support structure that we have already done. So no need to repeat that. Then if you give slice, so slicing is the topic which we have discussed last class. In FDM process, you do not have much provision to define your own slicing parameter. But tool path, so how to define a tool path? What is the printing pattern? Within each layer, how it is going to print. For example, if I give slice, so I have sliced. The timing is 1 hour 5 minutes. If you want to preview, Go to preview. The black color region is your support, and the orange color region is your path. So if you go further, so this is the model. There are 425 slices. You can see this. There are 425 slices. So this is the first slice. So see the pattern, how it is filled. What pattern? Could you able to understand what is the pattern of filling? So material is filled. What is the pattern? Could you able to see the pattern? The lines. At the core, it is a zigzag pattern, and the brim or raft is printed because that is a support. That is a contour pattern, right? So this is the first layer, second layer, third layer. Now what is the pattern? Now it is a triangular pattern. So you have a lot of options, which we I didn't discuss the triangular pattern. So triangular and zigzag together. You can see the pattern. Could you all able to see the pattern? The triangular pattern and the contour pattern, zigzag pattern. Then you keep on. So now the turbine is getting printed. So you have a skin. So two layer of skin, and within the skin I have a triangular. Why it is triangle? Because here I have mentioned 80%. So how to change a pattern? Go to edit. Under edit you have an option called infill. Infill is nothing but a tool path. How you are going to filling strategy. So here you have option. Instead of triangle, you have a cubic, and you can also work on octet. Zigzag we have discussed. Cross is nothing but directional. Gyroid pattern. Let us see gyroid pattern. Yes, gyroid pattern. So you can change different pattern. Different pattern have different property, because in different direction the material is going to be joined, and the joined direction will have different property compared to other property. So that is one uniqueness you are getting in additive manufacturing. You can customize your mechanical property in specific design or in specific structure. Then again, once you change the pattern, again you have to do slicing. So now you can see previously it was like a triangle, right? So now the timing is previously it was 1 hour 15 minutes. Now it is 1 hour 9 minutes. See, triangles are not visible within the turbine blade. Previously we have seen the triangles. Now the instead of triangle it is a gyroid pattern. Change from triangle to. Now again you can work on different pattern. Another important parameter with the toolpath is what is the percentage, because between one line to another line there is a space. Instead of 80%, if I give 100 in the sense whatever the material is there, 100% you have to fill. Highly dense component. Okay. Then again do slicing. Previously it was 1 hour 9 minutes, right? So now if you look, it is 1 hour 16 minutes. So already it is dense, even 80% and 100%, there is no issue. So now the spacing between one line to another line is still reduces. So that is another critical advantage in additive manufacturing. You can design your own porosity. If you look into the traditional manufacturing process, developing a porous component is very difficult. There are different methods employed for porosity, and within the porosity, within the same method, if you want to change the porosity percentage, then again you have to work on a lot of parameter. But in this case, in the design itself, you can change the porosity. Instead of 100%, let us say we will print with 30%, very low porous, high porous component, right? So after changing, again you give slicing. Now it will deposit very less material. only 58 minutes. So there is 15 minutes reduction in time. Obviously, the material consumption will also be less, and the strength of the component will also be less, but it is porous. You can use it for toughness. Now you can clearly see the pattern, gyroid pattern, sinusoidal pattern. Could you all able to see? So this sinusoidal pattern is nothing but gyroid. So, within the turbine blade, you can see sinusoidal pattern. So we will change some other pattern. We'll change to line. Again, do slice. So same 58 minutes because same fill percentage. Now the sinusoidal wave is replaced by lines, crisscross lines. So the line angle is also very critical. So still you can customize your own angle.